down, I'm substituting Gabriel, unfortunately for you guys, tomorrow as well. And from what I understand, Tuesday you finished off math estimation, and kind of got close to finishing it off. So you should all be experts by now. Right? No? Wrong? You should. All right. So what is this term? Anyone?
That's the play.
No one? That's the prior, right? So the whole point with map estimation is that you're embedding, so this is your data that you've observed given a set of parameters, and then you're embedding a prior. So you're kind of saying, I know something about this data, and I use this in order to make a better estimate of what my parameters are. And I won't go through the maths, you've already done that. But anyway, you end up with these closed form solutions, which are very good. You get those by using the conjugate prior and then maximizing the log, because the log doesn't change the position of your parameters, right? This is a monotonic function. So we end up here. So this shows the difference between using ML and using map. So here we've got loads of data. We've got loads of data points, and both ML and map come up with a sensible solution because you've got a lot of data that you can fit onto. Yeah, so the map is slightly different because it's considering this prior, but it's essentially very close to the data. Things change when you've got less data, right? So you see the map estimate is going more towards the prior. So you've only got 5 data points here, so the weight of the prior becomes more significant, and things start shifting more towards what you expected. And then we've got this situation. What's happening here? Anyone? Shout. Sorry? Sorry? Right, there's no variance. So no variance means there's no maximum likelihood, right? So the maximum likelihood is that your distribution of the one data value that you got is essentially infinite, and there's no variability. So that's not a very realistic situation, right? So ML doesn't work when you've got one data, but map still does. Whether it's giving you something sensible or not, that's questionable. But it's considering the prior and your data, and it will give you a midpoint solution between the two. Yeah. And then we've got the third way of doing things, and in some ways the purest way. Some people might say definitely what the computer vision book will tell you. So here you're computing a posterior distribution. Do we know what a posterior distribution is? Let's get my definitions out. Anyone? No? So posterior is something that is essentially a conditional distribution of your observed data. This is the observed data given a set of parameters, combined with a weight of some prior about your parameters. Yeah? So that's your posterior distribution. This is a prior, and this is your observations, given the full range of parameters that you may see. So it's kind of combining everything that you're observing. So this doesn't take into account anything that you've observed. So this is just a prior. And this is a new term that takes into account an observation that you've made, given your prior about the parameters. And then you're computing your posterior distribution, which will help you to make your prediction. The term here doesn't depend on the parameters, right? So it's fixed. That
terms of probability of observing some data.
Yes.
But if you have like a unlimited space that your data can include it, then that actually be used as value.
You have a limited space that your data can fall into.
Right, it could be, so it could take any value in a continuous state.
Sort of, but you already have some priors about your parameters, right? And you're assuming that your data fits within a particular distribution. Yeah? So, this is the equation that we had. What distribution are we assuming? So for this particular case, where we're working with a particular distribution. So you did that for ML and for map. So what distribution are we assuming that our data is part of it? So we've got a normal distribution with these parameters, the mean and the standard deviation, or the variance. And for our prior, what have we been choosing so far?
The conjugate.
The conjugate, right? And the conjugate distribution for a normal is the normal inverse gamma, which has got this horrible equation that I'm sure you can look at anytime you want to. But it takes 4 parameters, right? And if you multiply a distribution with its conjugate, what's the result? It's a conjugate distribution with different parameters, lambda constant, right? So this looks quite horrible, but it's relatively simple. It's just algebra about working through the way that the parameters change. So you end up with this constant, and with a new normal distribution. And this is one thing if you learn in this lecture. What's this thing called? Yay! I didn't know that. Okay, so you end up with this, and in order for the left-hand side to be a PDF, right? It means that these must cancel out. Okay? Because the PDF has to be behaving like PDF. So you end up with this. And I think it's on the next slide. It wouldn't. So it's not my area of expertise, but if you don't pick a conjugate, and this is one of the potential problems with Bayesian stuff, because in the real world, your prior may not be a conjugate of the distribution of your data, and then the solution to the Bayesian doesn't end up nice like this. It ends up horrible and often impractical or intractable to solve. Right? So Bayesians are great. The problem with them is that very often the real world doesn't behave the way that you're modeling it, and then you end up having to sum over infinite parameter sets, and that's just not possible. So here you have the equations for the way that you calculate the parameters. Essentially, given your parameters from the beginning, you're taking into account the number of samples that you observe, which is I, and then the mean of your assumed prior. I mean, it's kind of difficult to explain the way that each of these parameters behave, but if you want to go through it algebraically, it will probably make more sense to you anyway, and may help you to remember stuff in the exam. So once we've got our posterior distribution, which is this, we want to be able to estimate new values that we may observe, right? Which are these. So x star is a new value given a set of parameters. And the nice thing about, so the way that ML or map do this, with ML you're just seeing what you've observed, and you take the mean and variance of it, and that helps you to plug into your assumed distribution, and then you get your prediction, right? With map, you do something similar, but you're weighing predictions by your prior. The nice thing about the Bayesian approach is that you're actually not assuming any point prior, so you're not taking an assumption of the data, you're actually using the data and doing this weighing given the given the actual prior of your parameters, and you're weighing it by the likelihood, i.e. by the new observation that you made, and that gives you your posterior. And to estimate your prediction, you're actually summing the likelihood of a new value multiplied by a weight, and the weight is given by your posterior. So it's maybe a little bit tricky to explain, but it maybe makes more sense here. So you've got your parameters, your mean and your variance, and for each value here, you have a PDF, right? So if you take this one here, that's the map estimate, you end up with a PDF. If you take any other value, you end up with a bunch of PDFs, right? And with the Bayesian, you're integrating over the full range. So you've got your two integrals on either side, and you're essentially taking a weighted average of everything that you've observed and everything that you know, and you come up with your prediction. Yeah. Now you'll notice here that there's a difference between the map and the Bayesian, and it's the fact that the Bayesian is a bit more conservative with giving a high probability to your value around the mean, and the tails are a little bit longer, and that's kind of a classic thing about Bayesians. So they're not overly confident given the information, so they kind of allow you room to maneuver. Yeah. Why not? So I guess it depends on how many observations you've made, right? So if you've made 100 billion observations and your data, you've never observed a particular value, that value might be extremely unlikely, in which case you might not want to have any room to maneuver. And there are ways of potentially accounting for that. But let's say you've made 15 observations and you've just not observed a value. I mean, does that really mean that value will never occur? Not really. I think you'll see that in the next example. So one thing I should mention is that here, with this type of Bayesian, we are not assuming that we know anything about the mean or the variance, and there are ways of incorporating knowledge. If you know that the mean is fixed, there's ways of incorporating that, and the same for the variance. But I don't think it's covered in this lecture. I don't know if Gabe was planning to cover it later on. You can go online and find it out. So, to make your prediction or your predicted density, you do something very similar to what you've been doing before. We know that our observation was taking and we know that our posterior distribution is a normal inverse gamma. We know that the multiplication of these things gives us, because they're conjugates, we end up with something similar to the same form as the conjugate multiplied by a constant. What's this sign called?
Rove.
No. Anyone?
Inverse hat.
It has a name.
It's a gauges. It's called the brev, apparently, unless I got it wrong.
What?
B-R-E-V-E. Brev.
It's for
Yeah.
the same for breathe.
Oh, ages. And if it's the other way around, it's called something else. Something of interest for you. You can obviously take the constant outside of the integrals, and we know that the integral of the PDF is 1. Yep. So you end up with a constant, right? Subject to your parameters and your observation. And again, you can work this through algebraically. It will take a good size of A4 to, but it's not complex. Do we know what this is? So this is the gamma distribution, right? Have you done, you've done distributions already? Okay. So this is the gamma distribution, and gamma distribution is the conjugate of what distribution?
Yeah.
Is it?
It's not a distribution, it's a function. I think.
Well, a gamma distribution is very similar to a what? To a factorial, right? So I think a gamma distribution is the equivalent to this minus 1 factorial. So it would be a constant. And then you end up with the revised form of the parameters at the bottom. So this is illustrating the point before, but in a new curve way. You've got the map and the Bayesian estimate when you have a lot of training data. They're very similar. Yeah. And then as your training data becomes less, the map becomes closer to your assumed prior, and the Bayesian becomes less certain about your, what the situation is. And with one training example, the case becomes extreme. So the Bayesian becomes very, very uncertain, allowing you lots of room to play, to move. And the map becomes more and more certain towards the prior. And this is observing it on a log scale. So you see that where you have very little data, the map actually kind of stops at some point. It just says like those values are never going to happen. But the Bayesian doesn't. It actually assigns them higher probability, because you know that. So the second example we're going to work through is the categorical distribution. Do we know what that is? Not done categorical. Yeah. Right. So it's a discrete thing. You can think of it as you can take any number, a number of values. And each one has a particular probability. The important thing is that the sum of the probabilities is going to be 1. Yeah. And that's pretty much the important thing. Also, is there a real situation where this kind of distribution can occur? The die. Yeah. So I don't know why I put up 5 values here, because 6 is much easier to die. Yeah, a die is a classic example of this. And there's different ways. This way maybe looks more complicated, but it's actually easier to manipulate later on, different ways of writing it. But it's essentially a binning distribution, so you can express it graphically as a histogram rather than a continuous plot. Yeah. And then there's this one, which was really complicated. So Dirichlet distribution, which is a what of the categorical?
Conjugate.
So these are gammas, as we said earlier. Yeah. And the easiest way for me, anyway, to visualize this, I mean, over 5 or 6 values is quite difficult, but over 3 is potentially easier. So it's illustrated well in the book. This kind of plane cutting 3-dimensional space. So changes in the absolute values. So you see as they increase, they concentrate the spread around your expected value. Yeah. And changes in the relative parameters. So as the parameters change in a relative way, you can imagine the kind of like the orientation of this plane shifting around in space, and that changes the location of where your expected value is. Yeah, one way of visualizing it.
That's just a 3-dimensional shape.
This is just a 3-dimensional. Yeah. So So a dice would be, I can't imagine 6 dimensions. I don't know if one of you can, but it's pretty good. Do you want to do a picture? Yeah, that's, I'm sure you can work through the maths, but that's the general kind of way of imagining it. And then we've got the ML. So what do we need to do with the ML? So we've got our observations given a set of parameters, and we want to maximize the product of all of them. Yeah. Subject to, and this is important. So it's subject to the sum of all the parameters of all the likelihoods being 1. Yeah. So you've got your equation for the categorical, which is essentially lambda. You've got this n. Anyone with ideas about what this is? The n? Yeah, it's the frequency with which you've observed a particular value. Yeah. And then what do we do with ML in order to solve this? So do we try to find this directly? Take a look. Yeah. So we take the log, and is that enough? No, because we're not enforcing the condition that the sum must be equal to 1. Right? And I don't know if you've done this in the past, but do you know what Lagrange multipliers are? It's a nice way of expressing inequality constraints in an optimization problem, right? So your inequality or equality constraint is this, right? And a way of putting that in using a Lagrange multiplier is to have this Lagrange term multiplied by this. So this is essentially when you do the partial derivative of this term being 0 implies that this is true, that the sum of these is 1. I don't think we have time to go into exactly the way that the Lagrange multipliers work, but just take it to be so, and you can investigate in detail later on. And when you take the partial derivatives, you end up with this log likelihood optimized value of lambda, which is actually in the same position as your non-log optimization. And what does this actually express? So the parameter or the probability of observing a particular value is actually equal to the number of times you observe that value over the total number of observations that you made. So essentially it's just the proportion of times that you observe that value. Right? That's what the ML estimate gives you. So you're not incorporating any prior. Here you're just number of times observed over total number of times. No other information. So the map, you pretty much start off in the same way. What's the big difference? Yeah, we prior then, yeah. So you've got this. And what's the prior? If you're assuming that your data fits a normal. Not a normal, categorical. So it's very clever because you want the conjugate. Yeah. And then in this case it's quite straightforward. You end up with this, which reduces to that, which is simple algebra. Yeah. And actually this looks very similar to this, right? It's just the power that's different. So you've actually got the same thing plus alpha, the parameters of the Dirichlet distribution. So you may already be able to guess what the solution would look like. It would be very similar to your previous, the ML estimate, right? So it would be very similar to the proportion of time you observe, but you would have these parameters influencing, so giving a bit more information. Yeah. So we just have these. This is the ML, and this is the map. So we just embed a bit of prior information, but it's very, very similar. And in actual fact, if these are uniform, so if all of these are 1, which is essentially saying that the Dirichlet gives you no additional information because it's biasing everyone, and everything is biased in. Each bin is biased equally. Yeah, so that means that this reduces to actually just being the same as the maximum likelihood estimate. Let me check that I wasn't to say something else. I don't think so. And this is just an observation. So the top, just an example. This is your observed data. So this is the frequency that you're observing each one of these values. And this time it's got 6, so it could be a 9. Right? And at the top you're observing, these are just sample observations. Is there any pattern in these? No.
Yeah.
At least I can't
Some
see
of them?
Sorry?
In some of them?
In some of them.
Yeah, for example, C.
C.
It's only here numbers. Even the numbers.
Right, but don't look at patterns inside each one of these. Each one of these is an observation. So an internal pattern inside it is not really relevant. What you're looking for is patterns amongst the scope of these and then related to that. So that's the data that you've observed.
So what's
Are these observations in any way related to that?
Okay.
I mean, I can't see it, personally. The reason that you wouldn't be able to see it is because actually your prior is uniform. Right? So with the map estimate, we've actually given an equal bias to observing each one of these values. So essentially you have no information, you have no additive information. Your map estimate is the same as the maximum likelihood estimate. So your prior is not informative. That's essentially the illustration. How about here? Is there any pattern here? Right, and is 3 always bigger than 4 in there? Right, so with this one, with these observations, they look to have some sort of pattern resembling what you're observing in your original data. At least to me they do. I mean, 3 is always the highest, and they kind of follow this dip. 4 is always the lowest. So you have something that resembles what you're observing, yeah? And these are samples from a posterior. So that means they're samples from what kind of approach? Map? Posterior? Bayesian, right? Because Bayesian gives you a posterior given what you've observed. Yeah, so this is in a way coming before we've covered the Bayesian, but kind of to illustrate that the Bayesian will consider your data always. So let's go with the Bayesian. What is this? That's the prior, yeah? But it embeds no information about your observation. So this prior has no information contained in here. Yeah? It's just the prior, the distribution of the parameters. This, however, is information about your observations, and your posterior distribution is a weight version of those two. work through it in the same way. So the prior is the Dirichlet because that's a conjugate of the categorical. Yeah. And you've got your categorical, and again, conjugate multiplied by distribution is equal to something in the same form as the conjugate plus multiplied by a constant, and you've got your alpha tilde. And the constant, these two must cancel out for this to be a valid distribution. Yeah? So the period is essentially a Dirichlet with amended parameters.
Slightly tangential, but
Oh no.
no, it's not that tangent. Just, can you possibly at this stage use the fact that they don't cancel out to inform you that you picked the wrong distribution? Wrong in the data. So if they don't cancel out, then you go, oh, okay, I'll pick the wrong distribution.
I don't know. That's the answer. I would assume not, i.e. you're kind of potentially, I mean, in practice, if you're working with real numbers, they may not cancel out anyway due to effects of noise in your observations or so on. So I don't know how reliable it would be to use that. But you kind of, this is still in the derivation stage, so this is before you reach an answer. So maybe. I'm not entirely certain. What I was saying earlier, that when you don't pick a conjugate and you pick something else, you end up with much more complicated. You can end up with more complicated things. Then I guess you'd have to look back at that. That's like, I don't know. I need to direction for Gabriel on that one. Save all tough questions for Gabriel. Leave easy ones to me. Unless it's your right, so working through your posterior is Dirichlet. And then to get your predictive PDF, what do we need to do? We need to use the posterior that we calculated and estimate the PDF for each, something that's weighed for each potentially observed value over the full set of parameters that you may be observing. So it's this kind of integration over the full space. Yeah. And again, you work through it in very much the same way. So you substitute, that it's a categorical, it's a Dirichlet. You end up with this constant outside. So you get an analytical solution. And actually, the analytical solution is once again very, very similar to what the ML and MAP give in terms of the way it looks. Yeah. If you expand this, then it's a bit more complicated. But again, it's a proportion of number of observations over the total number of observations with a particular value, and then it's weighed by these terms, which are much more complicated with the Bayesian because it's more of the information. Sorry?
How we want to just implement that? How?
I think you'd open the book, or even better, you derive them yourself. If you want to have fun, late night, Thursday night, a couple of beers, and yeah, it's just algebra, but it can be tricky. In any case, it would be useful if you. But the thing is, if you do that for the whole book, then it may take you quite a long time. And so this is what I guess what you end up with in the end is that if this is the data that you're observing and your map and your ML estimates, they will follow the data. So that pretty much your PDF that you use to make predictions is entirely proportional to the frequency of observations. Yeah. So it has exactly the same form. And the important thing to note is that you've got 0 here and you've got 0 there. Right, so if you've thrown a die 15 times and you've never got a 4, your ML and your map estimates will say that you're never going to get a 4. So you'll never, the likelihood of getting a 4 would be close to 0. Yeah, I've noticed that as well. That was pointing, so that's why I said close to 0. But in actual fact, it probably would be subject to numerical. But the Bayesian doesn't do that. So the Bayesian is much more moderate in that way, and that's a good thing. Right? So the Bayesian tells you that even though you've never seen it, you may still get it. And it's much more definite about the favorite values. So to conclude, I don't know if I've gone too fast, because Gabriel said that you should go really slow with this. So essentially, I think the lectures covered three ways of fitting probability distributions and then using those to estimate incoming parameters, so to estimate new values. Okay, you've got your ML, which does what? Shall I start picking? Okay. So does ML consider any prior information you may have?
No.
No. Right? All it does is it calculates the mean and the variance of what you observed. And so it does a least squares fit. Yeah? Okay. The map takes a prior. Is that prior considering the full space of possible priors, or is it taking fixed prior? Fixed prior. Yeah? And then you've got the holy grail, like, well, maybe the favorite approach, and that's the Bayesian, which considers a very, I guess, computationally intensive or laborious way of doing it, but it takes consideration of all the possible priors or parameters over all possible observations, and it integrates over the full space, yeah? And you end up with a weight. So when you've got an observation, you're weighing that over the full space of possible parameters, and you integrate over it. So you end up with this. I think this is probably the best way to visualize it. This. So this is your posterior that you've calculated using this. And then for each value, you have a PDF. And then the Bayesian is summing up the weight average of all of these. Summing up the weight average, no, calculating the weight average. The average is the sum. And you end up with a more balanced estimate. What else can we conclude?
Nothing else.
We've worked two examples. Okay. So we've got the normal distribution, which I think we're doing a lot more about tomorrow. And we've done the categorical, which is your die example. So I've gone too fast, and we're kind of finished, so you've got ample time to grill me on any burning questions. Not a single burning question. That's disappointing. One, yes.
Sure, the slide before, that assumes that we had, he assumes uniformly distributed prior.
Here.
For both the Bayesian and
yeah.
the Bayesian pulled it in the right direction.
Yeah. So I think, I mean, I was looking at the equations earlier, but I kind of don't want to go through them on the board since I'm not confident with this. But if you know the means, or if you know the variance, then the Bayesian work, the equations work slightly different. You follow everything in exactly the same way. The derivations follow the same pattern, but you end up with slightly different results. And potentially that can be useful. So in a way, you're embedding very, very strong information that you may have about your data. Yeah, so you're reducing the complexity of the Bayesian. You're not asking it to do everything for everything. You're kind of saying, I know something.
So if you use the Bayesian to produce a distribution, so you essentially can rely on that distribution a bit more because you're less likely to get a result that then can't fit into that distribution.
You're less likely to embed an error which you're introducing by using one fixed prior. So you're more likely to consider a variety, it's more like a real world thing, right? You're more likely to consider a variety of options, or given an observed set of data, there may be various PDFs that fit that data to quite a good degree. It might not just be one, right? So the Bayesian takes into account that. It says, okay, there are lots of different distributions that this data could be coming from. So let's consider all of them and use that as a weight. Whereas the map doesn't. It just says, right, pick one. It's a really good one.
So in order to do the ML, all I need to do is go out and measure one thing once in one trial, and I can use ML to fit a distribution for that. With map, I need to have commission a study to go and do something and get me a prior, so I can then do my observation and base it off the result that that study produced.
Yeah, or very often with map, you just assume a prior.
Right.
So whether that's real world valid or not.
Like
if you're working in computer vision, you would very often assume a prior. Or you would calculate some priors based on some images that you generate and say, okay, well, my prior is this.
So then with the Bayesian, I need some observed data.
Yeah.
I need what's the other components that I need to gather before I can then apply the Bayesian? As in,
You don't need any of
is there
them.
kind of
With all of them, you need
examples?
observed data, right? Otherwise, you're not really doing anything. You're not doing any fitting, that's for sure.
No.
So you need to observe data.
With the coin toss example, I could, for instance, toss the coin and see what happens. Or I could assume that the coin is fair and use math. But then with the Bayesian, I would toss the coin and
You would have, so the important thing with the Bayesian is this term. Yeah. So this is a distribution of your potential parameters, which is not dependent on your observations.
so I would toss the coin and I would assume that the coin is
So you'd use a
somehow a based on a least distribution.
Yeah, so you've got 1 and 2. So you'd assume your answer is 1 and 2. Now what's the conjugate of
The beta.
Yeah. So you'd use that relation.
Okay.
Do I need to gather any data to be able to model my beta distribution? Is it just sufficient to make I will use beta distribution to model the linear distribution of the coin?
Well, in order to calculate your posterior distribution, you do need data, because here, so you say that this will be a beta distribution, yeah, and this will be, sorry, no, this will be the Bernoulli, this will be a beta. Is that right? No. Yeah, that's right. Just checking. And then, but here, you are taking into account your observed data.
So I still only just need one data set, and then I just make
As
it
long as
up.
you're not doing ML, one data set would be enough to give you something, but it wouldn't really inform you of any significant trends in the data, right? Because it's just one observation. I don't know. For me, one observation is not convincing about it.
Oh no, a set of observations.
A set, okay, so if you have a set of observations, then you can plug those in here. And what your posterior distribution should allow you to do is see whether the coin is a little bit biased or not. Yeah? So if your observed data is always heads, then your map estimate will basically say, right, you're guaranteed to always get a head. So you'll never get a tail. The Bayesian won't work like that. You still have a probability of getting a tail. But yes, you do need to plug in data, otherwise there's no fitting process. The whole point of fitting is that you're fitting PDFs onto some observations that you made. And you may or may not incorporate prior knowledge before you make those observations.
I think I was getting confused with prior as meaning like prior observations as opposed to prior guesses.
I think it is a bit confusing. I think, I mean, I would suggest it's good to look at the book and work out exactly what posterior is, what prior is, what likelihood is in the Bayesian sense, and then you kind of know what each of them means.
So how do we determine these alphas and these alpha briefs?
Good question. Yeah. I spent a lot of time wondering that. The reality is that I think you just kind of pick sensible values. So if you don't want to bias your solution, then you pick uniform values for all of them. Yeah.
So 1.
So uniform would be a 1. So in the categorical, you would pick a uniform distribution and say that each one is equally likely. But I mean that in a way that's incorporating your prior knowledge prior to your fitting. So you would assume that knowledge is about those parameters, right? That's the knowledge that you're trying to put in. It's knowledge of what those parameters are likely to be. It could be that the Dirichlet is a very good example of something that you know about your data, and you know that by setting as one of those parameters is 0, that fits very well to your particular situation. Yeah, you're making some sort of measurements like, I don't know, fishermen in the Atlantic catching cod, and you know that all fishermen are very sensible, and if cod is below 30 centimeters, they throw it back in the sea. So the guy that gets the cod on land knows that all cod will be above 30. So you may be able to set one parameter that signifies that small cod to 0, and then have a better estimate of what the fishermen are going to likely to be bringing in. That was a awful example.
How do you go from alpha to alpha brief?
Sorry?
How do you go from alpha to alpha brief?
That's a theory.
Sorry.
So I'm very confused about that. Basically, when you multiply a distribution with its conjugate, you end up with something that is in the same form as the conjugate distribution multiplied by a constant. And the new conjugate distribution has different parameters.
So you have to sort them out.
So yeah, I mean, you can look at the equations in the book. It's basically a standard way of showing it.
I don't understand the likelihood then. How can you do a prediction on xi given a set parameters? But you don't know the parameters exactly are.
So the good thing about Bayesian is that you end up, so this is the likelihood of observing this set of parameters. Yeah? And then given the way that you make a prediction is because you know what the distribution is. Yeah? So given you plug these parameters in here, and that gives you a prediction of x. Yeah? And then you multiply that prediction by the likelihood of getting those parameters. And by doing that for everything, you're essentially trying to consider all data. So all possible values of this x, given these parameters, multiplied by the likelihood of actually observing those parameters. Yeah.
Well, what I mean is you don't know that you don't have a fixed value for lambda 1 to 6.
No, so you'd be, so that's one of the problems. So in practice, where is it? If we go back to the normal, it's easier because it's looking at the intervals, right? You're multiplying this over the full set. So for every one of these values, so this is continuous, yeah, because it's a distribution. And for each one of these values, given what you have in there, I'm explaining this terribly. you don't understand how you can come up with.
What I'm saying is it seems that the first term is dependent on second. So they multiply together. I mean, I know they both make a probability distribution which you can find together. But it just seems to me that the first term is dependent on the values. Because that's saying.
But your end result is not a fixed value, right?
Yeah.
Your end result is a function. So you're calculating this over the space of all of these parameters, because that ends up on this end here. You're not doing it for one fixed.
What I mean is this, the likelihood term, mu and sigma squared must be fixed in order for you to follow the probability distribution of observing x given the circle.
I mean, this is just a derivation. You're not actually calculating each point in this. You're using that to get to here where you have a closed form solution. So you're not solving this. You're starting with, this is a concept rather than the actual final solution. That's the way I understand it. But maybe I'm explaining it really badly.
You should be able to just plug that in on the computer and work out the left-hand side.
But the left-hand side is this thing. So your posterior is, this is the posterior. So it's not, you're not working out the left-hand side, you're working out kind of the space of the left-hand side. It's a full function, right?
Yeah.
Over all of these parameters. So for a particular set of parameters, maybe, yeah, you work out one of them. So if you plug in a particular set of mu and sigma, then you will work out one of these, which will have this form, which will have this form. Yeah? But for the full set, it's this. And that's what you're interested in, because that's what will help you with your Bayesian. So, is that better? Yeah. Any other fires? Okay, so I think we're about done. So if you have any questions, but you don't want to shout in class, then I'll stay behind for a little bit. You can ask. And otherwise, I'll see you tomorrow for some more terrible explanation. Thanks.